Hey guys, we are going to start section 7.3 today. It's going to be looking at more equations that have logarithms and exponentials in them. So kind of similar to what we did in 7.1, we're just going to dive in a little bit more. So if you can remember back, we talked about the principle of exponential equality, where if the two bases were the same, then the exponents had to be equal as well. The first thing we're going to look at today is the principle of logarithmic equality, which is pretty much the same thing, but instead of exponentials, you're looking at logarithms. So it's saying that if your log with the base is the same, then the insides have to equal each other. So again, kind of a silly principle, because it's kind of obvious that if this is equal to this, then the two insides have to equal each other. So that's what we're going to be using today to solve some of our logarithm equations. So in order to solve some of these different equations, we're going to be using this principle of log equality and also the principle of exponential equality we learned back in 7.1, and then properties of logarithms that we learned in 7.1, expanding and condensing logarithms that we learned in 7.2, and then sometimes you can use your change of base formula if you need to in your calculator. So we do want to check for extraneous solutions though. We've done this in past units. That's because sometimes when we get our answers, we can't actually take the log or natural log of 0 or a negative. So if we get answers that happen like that, we need to throw them out. So don't go too quick and just get your answer and think, oh, I'm good, I'm done, circle it and move on. We do need to check and think, does that answer actually make sense and work in our domain? So let's look at a few examples. Let me zoom in a little bit here. Okay, so on this first one, we have the natural log of 30x plus 2 is equal to the natural log of negative 2x plus 66. So here's where you would use that principle of log equality. If both of them are natural logs and they're equal to each other, then it goes that the two insides also have to equal each other. So what we're going to do is essentially just drop the natural logs and just look at the two insides. So I'm going to say 30x plus 2 has to equal the negative 2x plus 66. And then from there, it's really easy to solve because we just have a simple equation. So we'll get our x's onto one side. Let's add the 2x over here. And then we'll just do this all in one step. Let's minus the 2 over to this side. So those cancel. So that we get 32x is equal to 64. And then if I divide by 32, we get x is equal to 2. And 2 is good. If we plug 2 back in, we get 30 times 2 is 60, and 60 plus 2 is 62. That's going to be greater than 0 and it's not negative. So our domain is okay. And same if I plug it into here, negative 2 times 2 is negative 4, 66 minus 4 is 62, which is positive, so we're good. So this answer is good. Okay, let's look at another one. On this one, we don't have logs on both sides, so we're not going to use that principle of log equality. You'll notice that when you have equations like this, where you have a log equal to a number and your variable is inside the log, what you're going to want to do is go to exponent form. So getting it into exponential form is going to allow you to get the x outside of the logarithm. So if you remember back to 7.1, if I want to go from log form to exponential form, whatever the base of our log is going to stay the base of our exponent. But then these two switch. So the negative 1 will become the exponent and the x minus 5 comes out. And we like doing this because the x is out of the logarithm. So now I can actually isolate it. So all I have to do is add this 5 over. We do have this negative exponent though. So let's look at that really quick. So remember, whenever you have a negative exponent, what that does is it's saying to take this and put it into the denominator, and then that exponent turns positive. So we get 1 over 4 to the power of 1, which is just 1/4. So this is equal to 1/4. And so now if I add my 5 over, you would get 5 and a fourth if you leave it as a mixed number, or if you want an improper fraction, you would get 4 times 5 is 20, plus 1, you get 21 over 4. Or you could do a decimal, and that would be 2.25. So Math Excel will tell you what format they want. They usually don't do mixed numbers, so most likely they'll ask you to do a fraction. Most likely an improper fraction is what I would do. So, but just look on your problems if they want a decimal or a fraction. Okay, let's look at another example. So on this one, we see we have logarithms on both sides of the equal sign, but in order to do our our principle of log equality, we can only have one log equal to one log. On this example, right now, there's two logarithms on this side, which doesn't work. But we learned last time that we can condense that. So if you remember back to 7.2, if I have a natural log plus a natural log and they are the same type of logarithm like we have here, if they're being added, I can condense those into one natural log, and this addition sign is telling me to multiply the insides. So it would be like I have, I'm going to put it in double parentheses, but x minus 3 times x plus 4 inside one natural log. And then that also, this 3 in the front, we can bring it back to being the exponent. So that way I have a natural log of 2 cubed. But now that I have just one natural log equal to one natural log on the other side, I can do that principle of log equality, where now I'm just going to take the two insides and solve with that. So it's like you're just kind of dropping the natural logs. So I have x minus 3 times x plus 4 is equal to 2 cubed. And 2 cubed is 2 times 2 times 2, which is 8. We do have these two binomials here being multiplied, so we are going to have to FOIL those. So we get x squared, I don't know why I wrote a 4, x squared plus 4x minus 3x, and then minus 12 is equal to 8. And then we can combine our x's here. 4x minus 3x is 1x. And then we have that x squared still in the front. And then whenever you have a quadratic, we always want it to be equal to 0. So I'm going to do this really quick on this step. We want to move this 8 over so that this is equal to 0 over here. So I have my x squared plus x, but then I will have negative 12 minus 8, which is a negative 20 over here. So whenever you're dealing with a quadratic, make sure you get 0 on one side when you're solving for x. So we had to FOIL this in order to get this negative 8 over here onto the left side to simplify that. But now that we have 0 over here, the only way to start solving for x is to refactor it. So I want to think what multiplies to be negative 20 and adds to be 1. There's like a 1 there. So if you want, you can do your little table. What multiplies to be negative 20 but adds to be a positive 1, and that would be 5 and negative 4. So 5 times negative 4 is negative 20, 5 minus 4 is 1. So if I want to factor this, we would get x plus 5 and x minus 4 equal to 0. And then from here, once we have it factored, you set each of these individually equal to 0, which a lot of you can just do in your head. We want to minus that 5 over, so we get x equals negative 5. Add the 4 over, we get x equals 4. And then again, we do want to make sure these work with our domain, especially on these ones where you get two answers. It's more likely that you'll have one that doesn't work with your domain. If I plug negative 5, there's kind of already a red flag there because that's negative. If I plug negative 5 in, I get negative 5 minus 3, which is negative 8. We can't have negative numbers inside our logs, so we throw this answer out. If I plug 4 in, 4 minus 3 is 1, so that's good. 4 plus 4 is 8, that's positive, so that's good. And then there's no x's in that one. So this answer is okay. So we keep this one, we throw out the negative 5 because it's not going to work in our domain. So again, we can't have anything 0 or lower. Okay, I think I forgot to check the other one. If we look back at our last problem, actually we do have a problem with this one. If I put 2.25 into our problem here, I don't know why I wrote 2.25. It's See, I need you guys to be in class with me so that you can catch my mistakes. 5.25, I'm getting like ahead of myself. If I put 5.25 into my logarithm, 5.25 subtract 5 is 0.25. And even though it's a really small number, it's still bigger than 0. So this one's okay. We're good there. But I forgot to check that one. I need you guys to catch my mistakes in class. Okay, let's look at a new one. I'm gonna kind of wall this off so we have some space. Hey, now we're looking at an exponential. So far we've only seen logarithms. We've noticed that our x is up here in the exponent. If I'm trying to solve for x and it's up here in the exponent, that's kind of tricky. So you'll also notice when x is in the exponent, you're going to want to go from log or exponential form into logarithm form. We want to get that x out of the exponent. So just like on this one, how we went from log form to exponential form, on this type of problem, to get the x out of the exponent, we want to go to log form. So it is a base e. Remember, e goes with the natural logs. So you end up with the natural log for that. And we wanted to actually get rid of this 50 first. So if I divide by 50, let's get this base e alone. We get e to the 0.035x is equal to 200 divided by 50, which is 4. So then now that that's just a base e, we want to go to log form. So when it's an e, we use a natural log. And then these two are going to switch places. So the 4 is going to come inside and the 0.035x comes outside. So that's how we get from exponential form to logarithm form when you're using a base e. I know it's kind of weird to remember that. I think going from a regular log is easier, but remember whenever it's an e, we use a natural log, and then these two switch places. So the 4 goes inside, the exponent comes out. But the whole reason we want to do that is now that this exponent's come over here, I can isolate x a little bit better. So I'm going to divide by 0.035. Zero, I guess. And now x is alone like we want it to. And we have this natural log of 4 divided by 0.035. And we'll just use our calculator for that. So the natural log button is next to the number 4. Let me clear all this out. So we get the natural log of 4 divided by 0.035, and we get 39.6. And they might tell you to do like tenths place or hundredths place. We'll just do the tenths place today, 39.6. And that would be your answer. And then exponential, if I plug that in, we're not as worried about our domain on that. You can have zeros and negatives and exponentials. It's only in logarithms, so we need to check it. So, hey, here's another one. So on this one, we have 25, which is an exponential here to a power of 2x plus 1 equal to 144. So again, when that x is up inside the exponent, we're going to want to go to log form in order to get that x out to where we can solve it. We have a base of 25 here, so if I go to log form, we're going to have a log with a base of 25, so that's your little subscript, and then these two change places, so the 144 goes inside the parentheses in the logarithm, and then the exponent comes out to what it's equal to, 2x plus 1. And again, the whole reason we like to do that is now x is out to where I can isolate it, so I can minus the 1 over and divide by 2. Here though, we do just have a number, a log base 25 of 144. You can just throw that into our calculator and get a decimal, so that way we don't have to worry about subtracting 1 from this messy thing. So I'm gonna just type this in. So again, you can either do the change of base form, which allows you to use this regular log button in your calculator. So maybe I'll show you guys how to do that again. If I have a log base 25 of 144, to use my regular log button, I would do log of 144 divided by log of 25. And that will give you this decimal right here. Or if you do have one of the nicer calculators, you can go into your math menu and then just scroll down to where you have that log base, and you can type in log base 25 of 144. But you'll see we'll get the same answer either way. So it's just kind of personal preference how you want to type it in. But I'm just going to take this decimal. We'll do 2 decimals on this one. 1.54 is equal to 2x plus 1, just because that's going to make it a little bit easier to start solving for x. Because now when I minus 1 over, we get 0.54 is equal to 2x. And then we'll divide by 2. And 0.54 divided by 2 is going to be 0.27. So x is equal to 0.27. And that would be our answer. So that's all the examples I have for today. Just again, briefly, let's look back at them. If you have a log equal to a log, you can use that principle of log form, of log equality, and just take the 2 insides and set them equal to each other. If you have more than one log on each side, like on example 3, you will first want to condense them so that you just have one logarithm equal to one logarithm. And then you can do that principle of equality and just take the 2 insides, but you have to have just one log equal to one log. So make sure you're condensing first if you have to. If you have a problem like this, where it's just a log equal to a number and x is inside the log like that, or if x is the base, sometimes you'll see it as a base, you'll want to go to exponential form first. So move to exponent form, and then x should be somewhere where you can actually isolate it and solve for it. And then on the flip side of that, if you have an exponential where x is in the exponent, you'll want to go to log form. So get to log form, because that will get the x to where you can actually solve for it. And just like this one as well, get to log form, x is now where you can get it along. So you will see all these different types of equations on your homework. Hopefully seeing kind of a variety of that helped. Let me know if you guys have any questions. You can email me, but your homework is just 7.3 on Math Excel. Hope you guys are safe and healthy. See you later.